Good morning. So today we will be talking about fracture mechanics. Next semester you have a full course on fracture mechanics. So in this course of mechanical behavior we will see it in a little rather summarized manner, not in full. Okay. So for fracture mechanics starting, we need to first have some concept of defects in a material, because we know that earlier also we have seen that due to presence of defects materials strength reduces. So in a structure, what I will have, if there is a defect, then the strength that has been proposed for a particular structure, or you can say that the material before using, we have some basic characterization test. So on that characterization we have some idea about the material strength, say the yield strength or the tensile strength of the material. So we have some idea about YS or TS of the material and some safety factor before application, that up to what extent of the strength level we will be doing the use of that particular material or component. Okay, so we have this idea, but even then due to presence of a crack, that's high limit of the stress for a material reduces. That also we can visualize that if in a material there is no crack, then with increasing time for a material the strength level won't reduce, isn't it? I can have some idea that for design purpose we have some particular strength level considering the safety factor, and with time the strength won't vary for the particular material. But if the defects are present, in that case what will happen? Now this strength level will go on reducing. For a material, if there is a crack, then during application, then the crack size will be increased, and due to that what will happen, you can see the residual strength here. So here you can write residual strength with time. The residual strength of the material with time will go on reducing. Okay, and there will be a certain moment when this crack length will be such that that particular strength is not there in the material, it cannot withstand the load, service load, and the material will fail. Okay. So what will happen is, in any application we cannot keep a material defect free. Earlier also we have seen, if there is a welding, so there is a crack, small crack, okay, and in some application it may be in a severe atmosphere, some atmospheric corrosion of the crack tip may be there. So due to that what will happen, the crack will always go on in increasing their size, and if this crack size increases, what we will find, that materials strength level what is there in it will be reducing, and if it reduces as well as the crack length is increasing, in this combination what will happen, there will be a certain time when the material will fail. Okay. If at that particular load material does not fail, then again the crack length will go on further increasing and the material will fail. Okay. So this is the thing. So from here we can have some idea, or from fracture mechanics we have to have the idea that, say this is the residual strength graph. If I draw this graph, say this is, as I have written, residual strength, and here crack size, or else time, So, if I have a residual strength graph like this, that means what? Now, with increasing crack length or time, you can say. So, at a particular instant may occur in the structure when the crack length is such that if there is any accidental maximum service load, the failure may occur, or if the crack length further increases, then in normal service load the material will have a fracture. Okay, this is easy to visualize. If you have any more problem in this graph, you have to, or rather you have to go to the book of David Broek, David. The book name is Elementary Engineering Fracture Mechanics. So, for fracture mechanics chapter, you can read Dutta or Hertzberg, but this book will give you much more input regarding the fracture mechanics what I will be teaching in the class. Many things I will take from this book. Okay. So, what we will find from here is the crack size, that is in which cases the crack size is very much detrimental, in which cases the crack size is such that due to accidental service load the failure of a structure may occur. Okay. So, before starting the fracture mechanics, what we can assume from fracture mechanics chapter? Now, what is the critical crack length? Or rather I can say that if you have some idea about the fracture mechanics, then you must know for some certain application what will be the maximum allowable crack length without failure. Okay. So, in this chapter what we try to basically find is this term, that what is the critical crack length for a material, as well as other things, what is the toughness level of a material, that is the fracture toughness of a material. Okay. We know that equation, right? If there is a crack, in that case something called stress concentration, isn't it? So, what was that equation? Sigma, oh here, two root c by rho, okay. This type of equation earlier we have seen. So, sigma max equal to sigma into 1 plus 2 root c by rho. That equation can you remember? Earlier I said. If anybody cannot, then this is the, if there is a crack in a structure, say this is the crack, then due to presence of a crack at the tip of the crack there will be stress concentration, and that stress can go to a maximum value, that maximum is sigma max, and this sigma is the normal service load, that is normal stress, nominal stress you can say imposed on the structure. So, if this is so, then sigma max equal to sigma into 1 plus 2 root c by rho. Rho is the radius of curvature of the crack tip. Okay. So, from here what we can see, that stress concentration, or rather the total stress concentration is dependent on the crack length. So, I can say that the stress concentration can increase with crack length. Can you follow this one? We have said that C is very much greater than rho. So, this 1 can be neglected. So, the stress concentration is sigma max by sigma, which is equal to 2 sigma root over C by rho. So, it is directly proportional with the sigma C. If C increases, that means the crack length increases, then the stress concentration will increase, and as soon as stress concentration will increase, then the crack will be much more detrimental with increasing length. So, what we can say, that the as the, or if I plot a crack length versus time. So, if we plot the crack length versus time, what I will see that the curve looks like this. That means what? Now the rate of growth in the crack length is increases with time. Do you follow that? Because of the stress concentration present in the material increases with crack size. So as the crack size little bit increases, the stress concentration is much more compared to the just earlier one. So next time further increase of the crack will be there at a higher rate compared to the initial one. So what we see that the crack length increasing rate, or rather I can say that increase in the rate of crack length is in this manner in a positive direction. That means if I take the slopes, these slopes will be increasing with time. Okay. So we can visualize that the presence of a crack for a structure is very detrimental. Okay. Therefore, we have a lot of stress analysis. Just if you have a crack ahead of the crack tip, how will be the stress distribution. Okay. So those stress analyses are there, and based on that we have all theories of this fracture mechanics chapter. Okay. So we need to know what are those stress analysis. Here I am just switching over to, you can say, the final equations. Okay, there are many basics on this, but those I am not incorporating in this syllabus, rather it is not there in our syllabus. So if there is a crack present in this, and then I have to do a stress analysis at this point, say. Say this is one crack in a body, and at a distance r theta I have to find out what are the stresses. Okay, this is a crack in a structure. At a particular point, what are the stresses present that we have to calculate. Okay, so I will have the sigma x term, sigma y term, tau xy term, etc. Sigma z term may also be there. What is that I will see later, but for the timing let us consider sigma x, sigma y, tau xy, what are those values. Okay. And again as I said that many basics are there, so that I am not incorporating. Okay. So the stress analysis tells that ahead of a crack tip at a distance r and theta, this sigma x, sigma y, tau xy terms will be equal to in this way, sigma root pi a, or rather this side as I have written. Obviously from the thing you can understand that at a distance r and theta the stresses will be dependent on this distance, because we know that stress concentration is maximum here, then away from this it will be little bit reducing, etc. So based on that I can say that the sigma that will be there away from a crack will be dependent on these two factors, the distance and the angle theta at which we are. Okay, so it is a function of r and theta. And then based on the analytical expression of Westergaard, G-A-A-R-D, based on his many explanations, what we find is sigma is related or the rather I can say that sigma y, sigma x, these values are related in this manner. Obviously, here also what I did not tell is this is one condition when the loading is something called mode 1 loading. Okay. What is mode 1, that I will just show you, plus note it down, please note it down, then I will show what is mode 1 loading. Actually I am telling this is the condition of stress distribution when I will have a mode 1 loading. Okay. And the calculation, as I said, I am not incorporating in your syllabus. Anybody interested can come to me, or if you see the Broek's book, it is given there. Okay, in our any of our notebooks like Dieter Hatchbach, it is not there. So you can read the Broek's book how we can achieve to this type of equations ahead of a crack. Okay. Okay, so this term sigma root pi a, you can see here and here both side I have written pi. There is some reason that sigma root pi a is known as equal to k1. K1, last class I think I have said this I is actually not ki. In all fracture mechanics chapter you will find this symbol I, and after telling repeatedly I tell, then also you make this mistake that call this as ki. So this is k1. Okay, in many cases I will require this equation, this symbol where it will be written as ki. So you have to pronounce that as k1. Why? As I said just now, this is in mode 1 loading. Okay, so we have to know what is mode 1 loading. There are 3 types of loading: mode 1, mode 2 and mode 3. So what are those modes are that we have to see? So the loading that we will be doing may be of different kinds. That means what? If I have a cracked plate, based on the applied load, why we will be varying the loading direction and all? Because for applications, right? For applications it may be different. In one case, so you have drawn, or you can see it now. If I have a crack like this in a plate, right? If it is a crack and both sides I am pressing it, so crack will extend. This is the mode 1 basically, nothing other than if I have crack here and in a perpendicular direction I am applying the force. Okay. So the crack length extension is perpendicular to the direction of the applied force. So that is mode 1 or opening mode. And then sliding means on plane shear. That means this is the crack, one of the surface is coming in this plane itself, coming down. This is the plane of crack and on the plane the surface is coming down. So this is known as on plane shear. On a same plane it is just shearing. In the same plane, just here you can see this, the top surface of the cracked part is shearing in that way. Okay, another may come in this way. So this is another type of loading. And third type is just there is a twisting kind of action. In this direction I have the crack, and that way out of plane shear you can tell. Second case on plane shear, and third case it is out of plane shear. So out of plane shear it is, that means a twisting kind of or tearing you can tell here is occurring. So that is the difference between these three types: mode 1, mode 2 and mode 3. Mode 1 is the most common for all loading and whatever fracture mechanics analysis we are doing, and our syllabus also will be reading only mode 1. Mode 2, mode 3, how are the stress distribution? Yes, this is similar to this, but little bit different, some difference is there. So those things we are not will not be reading, but the thing is, as per mode 1 loading, sigma root pi a is known as K1. This K1 is known as K1 or stress intensity factor. Stress intensity factor. Earlier what we have seen that something we have known as stress concentration factor. Stress concentration K1, this is sigma max by sigma, etc. That just a few minutes back I have written. So that is known as stress concentration, or you can tell that as stress concentration factor. And this one sigma root pi a is known as stress intensity factor. Okay, sigma root pi a equal to K1 as per mode 1 loading. But this sigma root pi a is not always the thing. Means what? Now based on the crack geometry, this varies. The value of K for mode 1 loading we call this as K1, but this value of K stress intensity factor varies depending on the crack geometry. It is dependent on sigma and A, that means the applied stress and the crack length. Along with that, it is also dependent on the geometry of the crack. Geometry means what? The position of the crack in normal surface is not defined. It may be just as I have done here, just on the surface. It may not be on the surface, it may be inside of a structure. It may not be a sharp elliptical crack, it may be a circular crack, or there is a circle, out of that a crack is growing. Hai. So based on this we have different values. So something like so it is simple to follow, that is K is a function of crack length and stress. Along with that we have written one term Y. Y is known as the geometric factor, that is dependent on the crack geometry. If the crack is a through thickness crack means what? Again is the question, like if I have, this is the plate on which at the center I have the crack and it is thick in this direction say, and throughout I have the crack. Okay. So if that is something like that, in that case I will tell it as Y, that is this geometric factor equal to root pi, or the one that I have written in that equation, K equal to sigma root pi A. If the crack is through thickness but situated at the corner, that is for this paper whatever I have done at the beginning, that is it is just at the edge corner, in any corner. If it is thick and one of this corner, say this duster, the crack is here. Okay, here is the crack and little bit inside deep. Okay, so this is through thickness crack, but it has started from the corner. Okay, do you follow this? In first case it was not at the edge but rather in between here, which I can see from here to that end. Okay, in the second case it is from here, and third case it is a crack, but that crack has started from a hole. So these are just three different things. Many others are also available, which I will see slowly, like only a circular crack. If it is, then what will be the equation? Okay, if the crack is situated on both ends, like crack may be to some extent in this plane as well as in that plane, it may be there. Do you follow this or not? Mane, say this is the one, so here also it is there also, it may be. Not that from here to the opposite end it should be. It may be here and little bit here. So both surfaces. So these are different crack positions, and based on that we will be seeing in fracture mechanics numericals that how these values are changing. Okay. Time for question. Pucho. Yes. What you have? No question? Questions? No. This chapter is not very easy. Please read and come to me with questions. ठीक है?